So now that we've reviewed oxidation numbers and we can determine whether or not a redox reaction is occurring, we need to practice how we go about balancing and writing redox equations. So we're going to, in this video, review some of what we looked at previously in Year 11 in terms of simple redox equations, and then move on to how we balance with more complex redox equations where we're dealing with organic molecules. So with this, we're going to understand that redox reactions for covalent compounds require a different process for balancing compared to pure ionic substances that we've seen in the past. Apply the rules for balancing complex redox reactions in order to balance those half equations. Apply the rules to be able to balance redox equations for the common oxidizing agents permanganate and dichromate. These are ones that you need to memorize the formula for, so make sure as we go through this that you make a note of these formulas. These are anions that you should be familiar with. Apply the rules to balance those redox equations for the oxidation of alcohols in acidic conditions. And in VCAR, we're only interested in balancing under acidic conditions. So you may recall that the overall equation when we go to balance a redox equation is broken into two half equations. Okay, so these two half equations, one will be for the oxidation process and the other will be for the reduction process. So we're going to have one where the electrons are going to have to be on the left-hand side, and then we want one where the electrons are going to be on the right-hand side, because we need to be able to cancel the electrons out when we come to bring the overall equation together. Each half reaction is balanced separately. Electrons are added to one side of the equation and then the other in order to balance charge. We compare the two equations to make sure the electrons lost equal the electrons gained. Identify the reactions in one where one is oxidation and the other is reduction. Finally, we can bring them two together and any spectator ions that were removed can be placed back in. The spectator ions, often when we're looking at these, we are just looking at pure ionic equations, so we don't need to worry about spectator ions. We can just remove those from the process, and often they're not even included. So if we look at the reaction between copper oxide and zinc, we have CuO solid reacting with zinc solid to form zinc oxide and copper solid. If we look for our conjugate redox pairs, we can see that the copper oxide will pair with the copper, the zinc will pair with the zinc oxide. So we're going to pull those out. So we have zinc going to ZnO, and we can see here this is going to be Zn2+, so we're going to have Zn going to Zn2+, plus 2 electrons. Okay, because this plus 2 is going to be balanced out by this minus 2. The charge over here is 0, so the charge over here is now 0. When we look at the copper, we can see that CuO, so this is going to be Cu2+, goes to Cu solid, so I need to decrease the charge on this copper, so I'm going to add electrons in and go Cu2+, plus 2 electrons, gives me Cu solid. So from this we can see that the zinc is going from 0 to plus 2, so the oxidation number increases, we have oxidation, and then the copper goes from plus 2 to 0, so we have reduction. So zinc is the electron donor. The electrons therefore are being given off by the zinc and they end up on the right hand side as a product. Those electrons are picked up by the copper, so the electrons are on the reactant side and the copper is reduced. So copper is the oxidizing agent, zinc is the reducing agent in this example. When we look at other reactions, such as the reaction between hydrochloric acid and magnesium, you may remember from our acid-bases unit, we said this is not an acid-base reaction in the typical Bronsted-Lowry. This is actually a redox reaction, and we can see that by the change in oxidation numbers. If we take this full balanced equation and write the ionic equation, so we're going to remove the spectator ions, Cl- in this case, from left and right, we get left with 2 lots of H+, plus magnesium solid, going to H2 gas and magnesium ions. We can see here that the hydrogen is +1, the magnesium is 0, hydrogen here because it's elemental is 0, and magnesium is +2. So we have hydrogen as one redox pair going from +1 to 0, so reduction, and magnesium going from 0 to +2, so this is going to be oxidation. I can now pull these two processes out as half equations, and I can see that I have 2H plus going to H2 gas. In order to make both sides equal 0, I add 2 electrons onto the left-hand side, making this my reduction half equation. And then magnesium solid is going to magnesium 2 plus. I need to add 2 electrons onto the right-hand side in order to balance that out. This will be my oxidation half equation. So that's our simple redox equations. So balancing just with electrons and using the atoms that we have. As soon as we start to look at molecules, things get a little bit more complicated. What we need to do is pull out the redox pairs, okay, write half equations for oxidation and reduction showing the conjugate redox pairs. Then we follow a set of rules for balancing the redox reactions, and we must do these in order. The mnemonic to remember this is COHES. K stands for key elements. These are all elements except hydrogen and oxygen. So any metal ions, carbon, anything like that. Anything that isn't hydrogen and oxygen is a key element. So this is key elements. O stands for oxygen. So once we've balanced anything that's not hydrogen and oxygen, we start with oxygen. Oxygen we balance by adding water. So if I have oxygen on the left-hand side and none on the right-hand side, I'm going to add water to the right-hand side to the amount of oxygens that I need. After that, we then move on to hydrogen. So we balance hydrogen by adding H+, because this is in acidic solution. This is what has to be in acidic solution. We have a source of H+ ions. Then we balance the charge by adding electrons. We multiply each half equation by factors so that we get the same number of electrons for each half equation, bring the two half equations together and cancel the electrons for our final balanced equation. And don't forget states. Our S is for states. Let's have a look at a couple of these examples to get you started so you can see what the process is. These rules become quite easy to remember if we just follow them in order and apply them every time. As you can see here, what we have is we've been given the dichromate, which is a strong oxidizing agent. You should remember that dichromate is always reduced to Cr3+. So in this case, we've got Cr2O7 2- going to 2 lots of chromium ions plus 3. This is our conjugate redox pair. Okay, for the oxidation process. You can see here we have 2 chromiums on the left-hand side, so we have 2 chromiums on the right-hand side. We have balanced the key elements. Next step is to balance oxygen by adding water. I have 7 oxygens on the left-hand side in my dichromate, so we're going to add 7 waters to the right-hand side. Then I'm going to balance hydrogen by using hydrogen ions. Because I've added 7 waters onto the right-hand side, I now have 14 hydrogens that I need to balance. There's no hydrogens on the left-hand side, so I'm going to add 14 H+ onto my left-hand side. Now I need to look at charge. On this side, I have plus 14 and minus 2, so overall it is plus 12 on the left-hand side. On the right-hand side, I have 2 lots of plus 3, so my right-hand side is plus 6. I don't want to make these 0, I just want to make them equal. So if I'm positive 6 on the right-hand side, and I'm positive 12 on the left-hand side, all I can do to balance charge is add electrons, which are negative, so I'm going to add 6 electrons, so that's the same as minusing 6. Now this is plus 6 on the right-hand side and plus 6 on the left-hand side. We add in states. Our ions are aqueous, H+ is aqueous, electrons have no state, water will be a liquid. And therefore we have a balanced half equation for the reduction of dichromate to chromium 3+ ions. When you apply these rules, they will work every time. You just need to make sure that you have double checked your charge and your electrons. The dichromate half reaction balancing comes up a lot in questions, so you should definitely write this one out as an example in your notes, as well as the permanganate MnO4- equation, as these are critical for you to know. Let's look at a couple of examples. So we've been asked to write the ionic half equations for the balanced overall ionic equation for the reaction in which manganese dioxide, MnO2, reacts with concentrated hydrochloric acid, HCl, to form chlorine gas and a solution containing manganese 2 ions. So if we write this out, what we've been told is that we have MnO2 is reacting with HCl to produce chlorine gas, which will be Cl2, and a solution containing manganese ions, so Mn2 plus aqueous. Okay, we're going to follow our Cohas rules. So I start with key elements. I have one Mn on this side, I have one Mn on that side, so everything is okay. And then I have HCl and Cl2. I clearly need to pull these out into two half equations, so I'm going to pull out my pairs. MnO2 goes to Mn2 plus, and then HCl goes to Cl2. I can see here I'm going to, let's start with manganese, Mn, that's all good. I can move now to O. I have 2 oxygens on the left hand side, none on the right hand side, so I'm going to add 2 waters. Now I've done oxygen, I'm going to do hydrogen. I have 2 lots of 2 hydrogens here. That means I've got 4, so I'm going to add 4 H plus onto my left hand side. Electrons now to balance charge, so I have 4 plus on my left hand side, 2 plus on my right hand side. I'm going to add 2 electrons to my left hand side to bring it down to 2 plus as well. Add in my states. So aqueous, 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 and liquid. This one would actually probably be a solid. Manganese dioxide will be a solid precipitate. Then we do the HCl. HCl to Cl2. Key elements, chlorine. I have 2 on the right hand side, 1 on the left hand side, so I'm going to multiply this up by 2. I have no oxygen, so I can skip that step, go straight to hydrogens. 2 hydrogens on the left hand side, 2 hydrogens on the right hand side. Balanced charge with electrons. There are no charge on the left hand side. I've got 2 plus on the right hand side, so I'm going to add 2 electrons to this side. I have 2 electrons in my oxidation equation and 2 electrons in my reduction equation, so they can cancel out. I can now write my overall equation as MnO2 solid plus, I've got 4 H plus here and 2 here, so it's going to leave me with 2 H plus aqueous plus 2 HCl goes to Mn2 plus aqueous plus 2 H2O liquid and plus Cl2, which will be a gas. And that is my overall balanced equation. As with everything, this requires practice, so I want you to do number B and put it in your notebook, and we will go through this example in class. Reduction of permanganate. Just like dichromate, it's a strong oxidizing agent, so the permanganate is reduced during a redox reaction. This redox pair is MnO4- going to Mn2+. So let's go through the balancing of this one. Make sure you write it down in your notes. we're going to have MnO4 minus going to Mn2 plus. Manganese is balanced. Using cohes, I'm going to now balance oxygen, 4H2O. Now I need to balance hydrogens. I have 8 hydrogens over this side, 8H plus over this side. Okay, now I need to balance charge with electrons. This is 8 minus 1, so this is 7. And then on this side it's plus 2, so I actually want to add 5 electrons to the left-hand side to bring plus 7 to plus 2. States. And we are done. Easy way to check if you've done this one right is what examiners always look for is the 8 and 5 over this side, because a common error is forgetting the plus 2 on the right hand side and therefore adding more electrons onto the left hand side than is actually required. So make sure you've made a note of this equation so that you can refer back to it later. This is another question. I want you to give this one a go, and then we will go through the solution in class. So you want to deduce the overall redox equation, so you have to break out in 2 half equations. Then you're going to have to determine which is the oxidation and reduction equation, identify the oxidant and the reductant, and identify the redox pairs associated in this reaction. So at the end of this, you should be able to know your rules for balancing redox reactions in acidic conditions, which is our cohes rules. Determine when these rules need to be used, i.e. any time we have hydrogen and oxygen in our equation. Basically, any time there's oxygen, you have to use these rules. You can balance the half equations for the reduction of dichromate to Cr3+ and permanganate to Mn2+. And that you can apply these rules of oxidation to organic compounds such as alcohols, which was our last question. We will have a lot of practice in this in class, so if you're thinking a little bit overwhelmed, don't forget to make a note of any questions that you have. Let me know what they are, send them through, or leave me a message, and we can go through those solutions in more detail. I hope this has made sense, and I'll see you in class.